What if I told you that the same principle firing in your brain right now is quietly running inside your phone's camera, your voice assistant, even the algorithm recommending your next video? Inside your brain, a biological neuron receives signals through branch-like dendrites, processes them in its cell body, the soma, and if the signal is strong enough, here's the key idea. A neuron doesn't just pass signals along, it sums them up. Only when that combined signal crosses a certain threshold does it actually fire. In 1943, two researchers, Warren McCulloch and Walter Pitts, be captured in pure mathematics. That question gave birth to the artificial neuron. The mapping is elegant. Dendrites become inputs. The soma's summing becomes a weighted sum, and that firing threshold becomes what we call an activation function.
But let's be precise. An artificial neuron isn't a tiny brain cell. It has no membrane, no ions, no biology at all.
So now that we understand the inspiration, it's time to build the actual math. Next, the perceptron, the first artificial neuron ever designed.
It starts with inputs, x1, x2, all the way to xn. Each one is just a number carrying some piece of information.
But each connection isn't equal. Every input gets its own weight, W1, W2, up to Wn. Multiply each input by its weight, then add them all up. That's the weighted sum. Z equals the sum of Wi times Xi. One more term joins the sum, the bias, B. It's not attached to any input. It's added on its own. That sum, Z, then passes through an activation function. The step function, below 0, 0, at or above 0, output 1. Put it all together, and that's the full perceptron. Y equals F of the sum of Wixi plus B. One equation, one decision. A large weight means that input matters a lot. It has strong influence on the final decision. Let's see what happens when we use a negative weight. A negative weight flips the story. That input actually pushes the decision in the opposite direction. And a weight close to 0? That input is basically being ignored. It barely moves the outcome at all. The bias isn't just an extra number. It's a shiftable activation threshold. It decides how easy or hard it is for the neuron to fire.
Without a bias, if every input were 0, the neuron could never fire. The bias gives it that independent nudge, on its own.
Geometrically, this whole equation is just a line, or in higher dimensions, a hyperplane, cutting the input space cleanly into two regions. Change the weights, and you rotate that dividing line, and they control its direction and slope. The bias doesn't rotate anything. It slides that same line away from the origin. Without it, every line would be forced to pass through 0. At first, the weights are just random guesses, a messy, useless line. Training is the process of nudging them until that line actually separates things correctly.